So, welcome back. In the last set, we looked at default reasoning, which is an approach which is close to logic, which allows us to make default inferences or defeasible inferences. So, inferences which can generally be made, but which could later be have to be withdrawn or defeated if more information comes. So, now let us look at another aspect of how you can go beyond first order logic, and we want to look at something called event calculus, which talks about time and change and actions, and see how we can reason with that. And we will also see some application of default reasoning here. So, this is what we started first order logic with. We said that the terms of a language, of a first order language, are essentially a set, this thing. So, they are either variables or they are constants, or you take a function symbol and construct a term, and we defined a set of terms using that. Then we looked at the set of formulas, which is what we are interested in. We saw that the constituents of formulas were terms. So, if T 1 and T 2 are terms, then T 1 equal to T 2 is a formula, atomic formula, but then atomic formulas and with connectives and all, you can get compound formulas. Or if T 1 and up to T n are terms, then we can give them as an argument to a predicate symbol, and we will again get an atomic formula. So, the point I want to make is that the arguments to formulas of first order logic are terms, and terms refer to objects in the domain that we have seen. Then we could apply the logical connectives, and we could get more formulas. So, this is the situation. We have the physical domain, which is what we are trying to talk about, and we have this language, first order logic language, in which we have predicates, and those predicates talk about things in the domain. But FOL cannot reason about many things, for example, actions or time. I mean, we can reason about time by adding time as an explicit parameter and manipulating it explicitly. Because time is like any other entity, but actions are not objects in the domain essentially. So, we will see this, and knowledge and belief essentially. So, when I say knowledge and belief, it says that what does one agent know about what does another agent do, but that is the last thing we will do in this course, and we will do it after we have looked at event calculus or uncertainty essentially. There are various approaches to handling uncertainty. Default reasoning was one of them. So, just a quick introduction to planning, because planning is to do with actions. So, there is a domain and there is an agent, and the agent has certain objectives, and the agent can perceive the domain, and the agent can act upon the domain. That is the general idea of what an agent can do, but there may be other events happening which are exogenous, or which there are other agents also maybe, but that is what an agent does essentially. So, a planning agent can perceive the world and produces actions designed to achieve its objectives. That is what a planning agent is designed to do. In a static domain, the agent is the only one who acts, but in a dynamic domain, there may be other agencies. So, we can model a dynamic domain by including other agencies that can change the world essentially. So, in the planning world, we work with predicates which describe the domain. So, for example, we have on table x, on x, y, clear x, holding x. AE stands for arm empty, assuming that we are talking about a one armed robot. This STRIPS was the earliest planning algorithm that was developed. and it worked in this domain of blocks world, and we look at 4 kinds of actions in this operators. So, you can either pick up something, or you can put it down, or you can stack something on another thing, or you can unstack it from there. So, those of you who have done the course on search methods for problem solving would be familiar with this essentially. So, in state space planning, we move from the given state to the goal state. So, the given state may be completely described, the goal state may be partially described, and we look at algorithms to do that. Anyway, that is not our goal here. Our goal is to, can we reason about logically about what is happening when actions are taking place essentially. So, here we have 3 blocks A, B, C, and we looked at this example when we were looking at first order logic, and that time we were concerned about some logical statements. Now, we are saying what will happen if this robot arm actually comes and picks up a block essentially. So, the given state is that A is on B, B is on C, as you can see on the top, A is on B and B is on C, and some color information was there. We are not so much interested about it here. The question is, when is this predicate true? Now, unlike in mathematics, once a statement is true, it is always true. In the real world, things like this can keep changing essentially. So, how do we handle that is the question. So, if the world is changing, then how do we capture the statements that changes in truth value? So, after an event has happened, the event is unstack A from B. As you can see, the robot has picked up A. What is true essentially? So, first of all, on A B is no longer true, and things like that essentially. So, as I said, in FOL we do not have this thing about things changing essentially, that something is true at some point and not true at a different point of time. So, we use the example of Pythagoras theorem, it is always true essentially. Once you have shown that it is true, then it remains true, but that is not the case for a statement like A is on B, because you pick up A from B and it is no longer true. So, instead of calling them predicates, we will call them fluents. These are predicates which can change in their truth values. In some sense, they are fluid a little bit. To reason about effects of actions. So, the planning algorithms do not really reason about that. They have their own algorithms to move from one state to another state. So, once you pick up A from B, for example, or you unstack A from B, then the algorithm would delete the predicate on A B from the knowledge base and add holding A to the knowledge base. So, that is happened in the planning domain. But if you want to talk about reasoning and logic, how do we handle this? We need to be able to treat actions and fluents as arguments to predicates. Now, remember, in first order logic, fluents cannot be arguments to predicate. We just said that in first order logic, only terms can be arguments to predicate, and terms refer to objects in the domain, whereas fluents are predicates like on A B, which have truth value essentially, and we cannot add them as arguments to predicates in first order logic. Yeah, so that is what we said, that arguments to predicates can only be terms, and terms are mapped to elements of the domain. We can circumvent this problem by extending the domain to include instances of actions and fluents. We add the symbolic representations of predicates and actions to the domain or the universe of discourse, and we say that we have reified the actions and predicates. We have looked at this process of reification when we create new kinds of entities and add them to the domain. So, now we are saying actions and formulas themselves or fluents will be added to the domain. So, this is how this world of event calculus looks like. In the physical domain, we saw that you can talk about FOL predicates, but the FOL predicates are now themselves arguments to event calculus. So, event calculus is a language which allows you to talk about time, actions or events and fluents essentially. So, these are relations between these three kinds of things. Sometime in the beginning of the course, we would have mentioned this. An example of event calculus: Yogesh made a cup of tea and left it on the table. Meanwhile, Smita saw the cup of tea and drank it. When Yogesh came back, he saw that the cup was empty. So, change is happening. The cup of tea was made, kept on the table, it became empty and things like that. So, reasoning about time, change in action is what we are interested in. After this, we will move to epistemic reasoning or epistemic logic, and then we will see that he concluded that Smita had polished off his cup of tea, and more importantly, Smita knew that Yogesh knew that she drank the tea. This kind of thing is captured in epistemic reasoning, and we will have a quick look at that after we are done with event calculus. So, what are the arguments to event calculus? The variables and constants of event calculus belong to one of the following sorts. So, when we say sorts, we also mean types. An event sort with variables, we will typically use E1, E2, E3 and so on. So, events include actions and events we will use interchangeably, but they also include exogenous events like rain, for example, in the domain, and we have already seen this. You can unstock a block, or you can walk from home to office, or Ramesh can walk from home to office, or Kumbhakaran can wake up, or there was a cyclone which was an event whose name was Nisha, it happened in 2008. The fluent sort, so the fluent type of things, that is what we do 3 separate sets of inputs to the event calculus. We will typically denote by F1, F2, F3 and so on. These are the predicates from the domain, like holding block 2 or location Ramesh office or awake Kumbhakaran. And then finally, the time sort or the time point sort. So, we have T1, T2, T3 and so on. These can be real numbers in a continuous event calculus, or they can be integers in discrete event calculus. So, what are the predicates of event calculus? Now, notice that these predicates take arguments which would have been formulas in first order logic. So, the happens predicate says that event E happened between time point T1 and time point T2. So, even E starts at T1 and ends at T2. Observe that it has a duration essentially. So, for example, happens eclipse 321 from starting from time point T5 to T7. We can create instantaneous version of actions by simply saying that the time start point and the end point is the same. Then holds at, remember that F is a fluent, and now we are saying explicitly that F is true essentially. When we looked at conceptual dependency theory, we had a flavor of this sort of a thing, which said that if you do this, then you are holding the book or something like that. That if X gives Y the book, then Y is holding the book. Now, this is in event calculus, we are trying to put this in a logical framework. So, fluent F is true at time point T. So, for example, holds at the form of glacier 17 is solid at time point T1. So, as you all know, glaciers all over the world and in particular in Himalayas, they are melting. We can also define a predicate called initially. A fluent was true initially, which means that whenever you start reasoning at that time point T0, that predicate was true essentially, which is holds equivalent to saying holds at predicate fluent F at time T0. Then the effect of events on fluents is captured by two predicates. One of them is initiates and what this says is that event E occurs at time t and results in the fluent F becoming true after time t. So, for example, the event of waking up initiates the fluent of being awake. So, we saw this awake and wake up. In discrete event calculus, so DEC stands for discrete event calculus. It means that the fluent F is true at time t plus 1, otherwise it says at time t greater than 2. So, terminates in some sense is the opposite of initiates, that event E occurs at time t and results in the fluent F becoming false after t. If you are talking about durative actions, which begin at a time t 1 and end at time t 2, we can define the fluent to become true or false at either end point essentially. So, for example, if you say that you are walking from home to office, then this will be terminated at the beginning of the action, that you are no longer at home, and the other event, that at office, will become true or will be initiated at the end of the action. So, we have a predicate called released. So, keep observing that the arguments to these predicates are arguments to the event calculus predicates are predicates from the first order logic. The fluent F is released from the common sense law of inertia at time t. What is the common sense law of inertia? It says that a fluent's truth value will not change unless initiated or terminated by some event essentially. So, we are making this statement that it is obeying the common sense law of inertia basically, which means that the fluent will change only if an event happened which changes it. But if we release it from this law, then we cannot deduce what the state it is in essentially. It is a mechanism to deal with certain kinds of uncertainty essentially. We do not have time too much to look into this, but you can imagine that, for example, if you were talking about tossing a coin, then there is a fluent called heads coin, and now essentially what you are saying is that whatever the state was when you were holding the coin, whether it was heads or tails, after you have tossed the coin, you cannot predict anything about whether it is going to be heads or tails. So, an event E can release a fluent F essentially if it happens. So, that is the predicate releases. So, here is a connection between two events. So, there are causal relation between two fluents. For example, on stove is initiated by light stove at time t, then the temperature of the water will be some increasing function of time is true after the time t this thing. So, that is talking about initiating, and they are saying that this relation has terminated essentially. So, if you put off the stove, then that relation will no longer be true. Let us look at some derived predicates. There is a predicate called clipped. So, sometime between time t 1 and time t 2, the fluent F is made false. This is equivalent to stating that there exists an event E, that event E happens at some time t, this t is between t 1 and t 2, and event E terminates the fluent. So, instead of saying this whole thing, we can simply write that fluent was clipped sometime between t 1 and t 2. Declipped is the opposite of that, it is made true sometime after this thing. Which is again equivalent to a longer formula. We can also say persist, which is like the opposite of clipped, between time t 1 and t 2. The effluent is not released from the common sense law of inertia up to that point, and it retains a truth value during this interval. This is a short form for not released at this thing. Okay, let us take a break and we will come back and continue our study of event calculus. It is a very brief study, but hopefully it will give us some insight.